Hi, I'm Daniel Chan from UNSW Sydney. This is Extension 3 Mathematics for talented high school students. In this video, I want to tell you about a very important test for verifying if a series is absolutely convergent. And this test is called the ratio test, which is summed up in the following proposition here. So suppose we're given some sort of sequence of these ANs here, and we want to sum this sequence to give you this series, the sum of the AN. So in this ratio test, what we do is we look at the ratios of corresponding terms in here. Okay, so suppose you look at the n plus first term, an plus 1 divided by an, look at the ratio of them, take the absolute value, and then we look at its asymptotic behavior of this ratio, so the limit of this as n goes to infinity, and that happens to be less than 1. If that's the case, then this series converges absolutely. And that is the ratio test. We're going to use it quite a lot in the following case where we look at power series. And this proposition gives us the following corollary in this case. Suppose now we want to look at power series, which means something like this, okay? Something of this form, sum of anx to the n. It's like an infinite polynomial. And the coefficients are given by a sequence, the sequence of an. Now what we're going to do is we're going to look at the ratio of the coefficients, the consecutive coefficients, but we'll look at it in the reverse order. Okay, we'll look at an divided by an plus 1. We'll look at the absolute value of that and take the limit as n goes to infinity. And we'll call that r because this is often called the radius of convergence for this power series. And why is it called the radius of convergence of this power series? It's because when you look at this, okay, so this will be a series for every possible value of x. This will converge absolutely for every value of x whose absolute value or modulus is less than this radius of convergence. And that's a corollary of this ratio test here. Okay, so let's just get a bit of a feel for this corollary by looking at some examples, and then we'll show you how this corollary follows from the proposition. We'll prove the proposition last. Okay, so for example, let's do a little sanity check and see what happens when all the ANs are equal to 1. When all the ANs are equal to 1 here, what you'll find is that this is just the geometric series, and this will converge when the absolute value of x is less than 1. If all these ANs are 1, then of course these ratios are just 1 to 1, they're just 1s here, so this radius of convergence is just 1, and so we have the result that we already knew. The geometric series, okay, of just the sum of the powers of this x will converge for all x of absolute value less than 1. Suppose now that instead of using 1 as all the coefficients, we change them to something bigger. And we're going to sum n times x to the n, okay, as n goes from 0 to infinity. Then, well, does this converge absolutely for values of x other than 0? Okay, well, we can try to apply this corollary and see what happens. Okay, so let's have a look at the limit as n goes to infinity. If you look at the nth term, the absolute value of the nth term to the n plus first term, and as this goes to infinity, of course, these approach each other in the sense that the limit of this ratio, at least, is equal to 1. And what does this imply then, this corollary here? That implies that a of x converges absolutely if the modulus of x is less than 1. Okay, so that's a rather nice fact that you have, okay? Whenever this modulus of x is less than 1, okay, so just like for the geometric series, okay, it converges for all those same values. Okay, so now let's have a look at the proof of this corollary, assuming that the proposition is true. Okay, so we're allowed to assume that this last condition here, so if the absolute value of x is less than r, then we're just going to apply this proposition to this series here. For each value of x, this gives you a series. And we'll just have a look at that. So let's have a look at the limit as n goes to infinity of the n plus first term, which is a n plus 1 x to the n plus 1, over the nth term, a n x to the n, the absolute value of that. And so what's that going to equal to? Okay, so I guess what you can do is you can cancel x to the n on the numerator and the denominator to give you an x. So there's an absolute value of x here, times the limit as n goes to infinity of a n plus 1 over a n. And what's this equal to? Well, here we're going to assume that the limit of a n over a n plus 1 is equal to r. So the limit of this is going to be 1 on r. So this is just the absolute value of x divided by r. And we said that this absolute value of x is less than r. So that means that this ratio here has to be less than 1. And then now we can apply this. This ratio here is less than 1. So it does converge absolutely. And that gives you the proposition. And we are done with the proof of the corollary. Okay, so now let's prove this proposition. So this proposition is proved by a classic epsilon type argument, which goes as follows. So firstly, we're going to have to use this condition here on the limits of the absolute values of these ratios. Okay, so what does a limit mean? A limit means that if you go far enough out, okay, so for sufficiently large values of this n, okay, so suppose we say sufficiently large means that for all n greater than or equal to this m, this natural number here, you will be within epsilon of this limit, whatever that positive epsilon is. Okay, so that's the level of closeness. So let's have a look here. So we've got we're going to pick an epsilon, and what type of epsilon are we going to pick? We're going to pick one with a special property. So this limit is less than 1. So even if we add a small positive number to it, it will still be less than 1 as long as that small positive number epsilon is small enough. So that's what we'll do. We'll take this limit and we're going to pick an epsilon small enough such that even when you add epsilon to this limit, it'll still be less than 1. And what we're going to do is we're going to go far enough out so that this ratio is within epsilon of the limit. So what does that mean? So far enough out means that we can find some time, say m here, such that for n greater than or equal to m implies that this ratio here is within epsilon of the limit. So the ratio here, the absolute value of a n plus 1 over a n, is within epsilon of this limit. And if it's within epsilon of this limit, that means the biggest it can be is this limit plus epsilon. So the biggest it can be is this r. So this is less than r. Okay, so that's when you go far enough out in this sequence for n greater than or equal to m. So what does that imply? Okay, so for these values, what can you say about this an, or its absolute value? Well, when you go from one term to the next after the nth term, okay, this ratio less than r means that how much bigger can this an plus 1 be? It can be at most r times bigger. So that means that this is bounded above by r to the n minus m times the absolute value of am. Okay, so this gives us a bound on the tail of the sequence. That's how we want to think about what we have here. Okay, this is bounded. And basically the way you should think about it is this is bounded by a geometric series whose common ratio here is this r, and this r we chose to be less than 1. Okay, so that's the secret to what's going on. And now what do we do? So we consider increasing a sequence of partial sums. What's the increasing sequence of partial sums? We want to show that this converges absolutely. So we want to look at the absolute values of these terms, and we want to look at the sum from n equals 0 up to, say, some big capital N. and we want to take the limit of this, and we want to show that the limit exists. Well, this is an increasing sequence, so to show that the limit exists, we just have to show this is bounded. So let's bound this, and let's suppose this n is at least as big as m, because of course you only need to see what happens as n is big. Okay, so let's bound this, and how can we bound this? Okay, so we'll bound this as follows. So firstly, you can look at the first m terms. So let's look at the first n terms from n equals 0 up to m of the absolute value of an. And then you have the rest of the terms. Okay, so let's add the rest of the terms here. So this is the sum of n equals n plus 1. And so forth up to n. And then the absolute values of those an's though are bounded by this term here. The absolute value of an times r to the n minus m. And it doesn't matter if we add extra terms, so we can go all the way to infinity here if we like. That'll only make this right hand side even bigger if we go past this n here, because we're adding more positive numbers here. And the key point is that this right hand side is bounded. It's a finite number. Okay, this is finite because here we have a infinite geometric series whose common ratio is r, which is less than 1. So this converges to some finite positive number, and this here is just a finite sum. So here we have an increasing sequence of partial sums, and this increasing sequence is bounded above, so we know it has to converge, and that gives us a proof of the ratio test. I hope now you can also use the ratio test to test for convergence.